before my time, some of the first laser power measurements were actually for laser safety purposes. When people started using lasers in those grocery store scanners, they wanted to make sure that the amount of light was not hazardous. So that's a key accomplishment, and the group has continued over the course of the years to play an important role in standards development for laser safety purposes. We've developed new standards to help the semiconductor industry, and for that my group won a Department of Commerce silver medal. So if you can remember, in the late 90s there was this big jump in the processing speeds of computers from megahertz to gigahertz, and at that time they shifted from printing those circuits with lamps to lasers to get to smaller feature sizes to make faster chips. There was a dearth of standards at that time that were accurate enough to enable those measurements. Measurements of light are much more complicated because there are lots of different parameters. There's visible light and what we call ultraviolet light and infrared light, so there are different wavelengths. There are different power levels of interest, from nanowatts that you might have in a communication system to kilowatts, which is the kind of power level that you might have. You need to know the power at the end in order to know whether or not a signal was transmitted from Boston to Los Angeles on the fiber backbone. Those laser power measurements are used as part of the sending that signal in that moment, but it's also part of the qualification of those components to make sure that they can actually be used for that. So one of the things that we've been working on for years is to come up with a material that has the same response independent of wavelength, and that converts that optical power into a thermal or a heat signal. And that's a very black substance. And so in recent years, a team led by John Lehman has made enormous progress in making these very black, very uniform surfaces out of carbon nanotubes. And it's a pretty amazing material because it works over 15 decades in power, depending on the geometry of the tubes and how they're deposited onto the surface. But it also works over many orders of magnitude in wavelength as well. It's really sort of our universal absorbing substance, so that at some point in the future we might have one detector that works over all these different wavelengths, where right now that's represented by a whole suite of different types of optical detectors. One of the things that I love about working at NIST is every day is a little bit different, and there are so many different aspects of my job. I spend a lot of time talking to customers who have measurement problems, and they're always new and different and challenging and make us scratch our heads, and it's very satisfying to feel like you're helping somebody with their manufacturing process or safety in say a medical situation or something like that. So that's one thing. I like building things and I like taking things apart, so that's another very satisfying aspect of my job. And we also, a third would be actually the career development of young people, being mentors to a variety of students and postdocs and junior staff who've come here, from high school students to PhDs, having them come back years later and telling us how successful they are. I really enjoy that as well. So in a recent study that we did of over 100 lasers, what we found, in fact, was that 9 out of 10 green lasers failed, were inappropriately labeled, were actually emitting more power than what was allowed by the Code of Federal Regulations, and half of all red laser pointers also failed, were mislabeled, meaning that they had more power. So in the hands of somebody who is not aware of appropriate use of powerful lasers, could in fact hurt themselves.